What do we know so far on our lab? Okay, so the inner part number, we came up with what? And what is this guy? This is, what's DZ on this guy? 5.1, right? Plus minus 5%. We okay? Everybody okay on that? Okay. So what sides have we chosen for RS? $100 ohm. Let's go back and check that. So that's not what I came up with. So what's the N max? What's that? Can't be 1.9 because it's got to have over 5 volts. What's the maximum input voltage? It can't be 1.9 because I've got it's got to be greater than 5. I'm not. This is not VRS. This is the maximum input voltage. Yeah, VN max. Okay. No, VN minimum. 6. Okay, so VRS max would be equal to 1.9, right? VRS minimum would be equal to what? Which we don't say, right? We say 900 millivolts. Okay. So we want R, and then my load current is, my I of the load goes from what? What's that? Yeah, the minimum maximum load current. Are we okay? Everybody okay so far? So, and by the way, guys, you got to show your calculations on these, right? On the worksheet. Okay, so RS, and we need to look up IZK. What's an IZK for a? What's IZK for a 1N4733? Okay, so everybody okay there? Any questions? That came off the data sheet, right? Everybody okay so far? So RS means it drops the minimum voltage, which would be 900 milli, at the maximum current, which would be, okay, so what we need to do, we got, so VRS, so maximum current would be what? Maximum load current would be 7 milli plus IZK, which would be 1 milli. So that's 900 divided by 8 milli. Is everybody okay? Okay, is that what it came up to be? Huh? Okay. Oh, that's what's going on. Okay, so we came up here and chose an X standard value, which is what? And then we checked the tolerance, right? Of 1.05. What does that give us? Okay, so this guy right here is fine, right? So 100 ohm is good. Everybody okay? All right, so what's the next thing we're going to do? 100 ohm. So RS, we're going to choose 100 ohm. So what we're going to do now, we need to figure out PRS. What's PRS? What's that? Just answer, yeah. Are we okay? Everybody okay so far? Yeah, 1.9 squared, or you could calculate the current, right? So you could take 1.9 divided by 100, right? You understand that? So it's whichever formula you want to use, because we're going to have to calculate our IRS max anyway, right? Sooner or later. Okay, guys. So then we're going to hook up our circuit. It says we're going to come over here and we're going to use our 100 ohm resistor, which I got to go find one. And then our Zener is going to be in there like that because it's a positive supply, right? Everybody okay? Okay. And then we're going to come over here and we're going to have to vary the current. So we're going to try to set up a circuit so I can not only do this. So what I'm going to do over here is I'm going to use the trainer's variable supplies. So I can change this between what? 6 volts and 7 volts. Everybody okay? Now I've got to come up with a circuit where I can vary the current. So what we're going to do is, what do we use to vary current? What device can we vary current with? But it's got a name. Well, not a rheostat. But what did I tell you? So we got two ways we can use a pot as a rheostat. We can come over here and do this, and now this is a pot to act like a rheostat. Or you could come up and you could do this, and you take your output off there. Now, what's the problem with using this is you've got an antenna sticking out in the air, right? You understand that? And it becomes very noisy. So this is the preferred method right here. So what I'm going to do is I'm going to go over here and use a 100 ohm resistor so we don't create a short circuit, right? And then I'm going to come over here and I'm going to use a pot wired to the rheostat. So now we can adjust the current. The maximum current we could get is if we let that guy drop all the voltage. Now, we got to measure current. So how am I going to how do we usually measure current? So we got two nice resistors here. So how do I usually measure current? Normally, back at DC, you learned you broke the circuit and put your meter in series. But we don't have to do that. Why? Two resistors that we know their size. So instead of breaking the circuit and measuring current, we can measure the voltage across the resistor. 100 ohms is 10 milliamps per volt. So a lot of this math we can do in our head. We don't have to. So now if I want to measure the load current, I can measure across this resistor. If I want to measure total current, then I can measure what? Across the voltage across that resistor without breaking the circuit. So you learn real fast that to measure current, we can measure it directly by breaking the circuit and putting our meter in series, or if we can find, Yeah, 'cause that's the guy. That's the guy. That's the series resistor. And what's constant in a series in a series is the total current, right? So what we're saying is the total current that flows from this power supply, no matter which direction you draw it. It's easier to see if you draw using a conventional current flow instead of electron flow. So in this, we're going to use conventional current. So conventional current flows, guys, y'all understand that? Current flows. And of course, when they originally came up with current flows, by the way, what's negative and positive? Negative positive is something that the guys just came up with, right? And originally, they thought that the positive was the most positive potential. I mean, was the highest potential. So originally, when they developed all these dang symbols, so when they came up with a symbol for a diode, guess what they used? They used conventional current flow because that's the way they thought. So originally, a conventional current flow, we say current flows with air. But electron flow, it flows what? Against air. But current flows. It don't change any of your math. So whether you use conventional current flow or whether you use electron flow, it don't change any math. The top of the resistor would still be positive and the bottom of the resistor would still be negative no matter which one you use. So when you see these solid state circuits, it's easier to try to visualize what we call a positive current flow. If I can get to the black one, I can. So that means all my current that flows out of this power supply goes to that resistor, every bit of it. So if I wanted to calculate total current, all I have to do is measure it across that series resistor. We call it RS, which means series resistor. Now, when it gets over here, what does it do? It splits. It splits between the what? The load and the zener. But I know I can calculate total current. So what I can do, instead of measuring total current, I can say I total would be equal to what? VRS divided by 100. Without doing what? Without breaking the circuit. Over here, this is my load. So I've got a series resistor right here. So that means all the current flow through this has to go to that resistor. So I can calculate I, the load, by taking what? V across this resistor. We're going to have to give it a name. And so we'll call it VR1 divided by 100 ohms. And that will give me my load current, right? You understand? And it's 100 ohms, so it's 10 millivolts per volt. So a lot of times we can do this without what? Without math. I like 1K. 1K is 1 millivolt per volt. 100 would be 10 millivolts per volt. Okay. So we got our circuit, except Rich has got the wrong size resistor. So let me go find a 100 ohm resistor. So what's the color code for 100 ohm? Not black. Not brown, black, black, brown, black. We By the way, guys, if you was taking my class and you had to do this garbage right here, let's see. See what this guy, see what they did. I can't get my camera to, I need to start this over. Look what they did. You'll see, look what this person right here did. So we got two cameras up here. One of them is pointing at the circuit, and one is pointing at my meters. So I've got the yellow one, the Sperry. It's going to be across a 100 ohm resistor that we're going to calculate our load, and then this guy right here is just one I'm going to use. So across the circuit, where did I do it? Well, where did I do the measurement across the circuit? Yeah, the total circuit. Okay, that's one lead. Okay, so where would I measure my applied voltage at? Huh? Okay, so that's one lead, right? Where did I put the other lead? That's not total. That's not total voltage to the circuit. That's the vote. Yeah, isn't that what we're going to do? What does the procedure say? Okay, so where's my input voltage at? Right, but it's going to be right here, right? There's my input voltage, not across the resistor, across the power source, or I could do it here, right? Understand? Okay. I'm doing that wrong. I shouldn't do that. So all I'm going to do is just come across here, right? From black to here, to this side of the resistor, and turn the power supply on. So what's the minimum voltage we're supposed to measure? Did it say set it to the minimum? Okay, what's the minimum? No, the minimum input voltage, not the RS. Okay. We're setting our input voltage. I mean, this is a good question, guys. So I'm setting my input voltage. So I need to not. So I'm setting my input voltage. So this is DN right here. This is DN right here. Okay. So I have my meter lead. I have it on this side of this resistor, and then I have it on circuit common. Okay. Right. And I'm setting this to 6 volts. Y'all understand? Everybody okay? Yeah. So to set my input voltage, what I'm going to do is I'm going to change my power supply. Okay. So this is common down here, so y'all can see the placement of my meter leads. I'll just do it across the circuit. So here's the circuit right here. So here's the bottom of the Zener. So there's the common. I'm going to come over and put it on the top of my resistor right there. So this is where I'm making my meter read. Now I could also put my black lead right there and go right there, right? Understand? Okay. But I'm going to come over here and I'm going to put it across the circuit. Everybody okay? And then, of course, now I'm going to come over here and look at my meter, and I'm going to set this voltage until that's 6 volts, which is this guy right here. So this is the voltage drop across my series resistor. I'm gonna turn this up. I'm actually turning up the variable power supply, and I'm setting this to as close to 6 volts as I can get. That's pretty good, right? Woo! All right, so okay. Okay. Now what are you supposed to do? Okay, this is the voltage drop across my 100 ohm load resistor. 98 point or 99 millivolts. No, it's not V out. That's the current. V out, where would I read V out at? Or across the Zener too, right? Okay, because the Zener's in parallel. So this is the load. This is the voltage right here. This is V out with V in minimum. No, that's not I of the load maximum, right? That resistor to get the maximum current. What's our maximum current? Are we doing maximum current first or minimum current first? Okay, so what voltage V is equal to what? I times R. So I come over here, I say V, and what do we need? What current do we need? 2.5 milli. What size resistor? 100 ohms. So what voltage do I need to cross that resistor to get 2.5 milliamps to flow through that resistor? Y'all understand that? Did I lose anybody? Yes or no? What we're trying to do is we're trying to set our load current. We're trying to set our load current at 100 milliamps. I'm sorry, 2.5 milliamps. Okay. But I'm measuring the voltage across a resistor. So I'm trying to figure out, okay, how much voltage would the 100 ohm resistor drop to conduct 2.5 milliamps? Everybody understand that? So how do I calculate volts if I know current and I know the size of the resistor? What's the formula? Not for voltage. That's power. Okay, y'all understand. What we're trying to do is I'm trying to get 2.5 milliamps to flow across that resistor. Because that's my load current, right? You understand? Well, what do I need to calculate? But I'm going to measure voltage. So what do I need to calculate voltage? Using Ohm's law. Voltage is equal to what? I times R. What do I know? Well, I know the current I'm trying to get. What's the current I'm trying to get? I'm trying to get 2.5 milliamps. What size is the resistor? 100 ohms. So when this resistor drops this voltage, that means there's 2.5 milliamps flowing through it. Okay, so what I'm going to do is I'm going to adjust that rheostat until I get what? 250 millivolts. When I get 250 millivolts, that means there is what? 2.5 milliamps flowing through that resistor. Do y'all understand? Okay, so this is the yellow meter. So it's hooked up all the time. So what I'm going to do is I'm going to come up here and adjust this till I get what? 250 milliamps. I mean, I'll start 250 millivolts if I can, as close as I can get it. That looks good. 250 millivolts, so that means I have 2.5 milliamps flowing through that resistor. So that's my load current. Y'all understand? This is the minimum, right? Ooh, something's going on, guys. Because this is not going to work. And we've done this lab before. What the resistance we know the size of the resistor. Guess what? 100 ohms. We know the voltage drop. We know the current we want flowing through it. Okay, 2.5. Yes, because we're measuring volts, right? That makes sense. Any questions? Yeah, we just calculated it. So y'all, first of all, do y'all understand what we're doing? Does everybody understand what we're doing? Yes or no? Bernard, you're okay. You're kind of looking. We need a load current of two. We need a load current of 2.5 milliamps. Now I got two options. I could put my meter on amps. I could break my circuit and I could put my meter in there and use an amp meter, but I don't have to do that because I've got a resistor. Not only do I have a resistor, I have a 100 ohm resistor, which is pretty neat, right? You understand that? So what we did is I said, okay, I'm trying to set my load current to get what? 2.5 milliamps going through my load. So what are we doing? Well, I said I know, but I'm going to do voltage. Voltage. I'm going to measure voltage and calculate current, right? You understand, or vice versa. So I'm saying, okay, what voltage would a 100 ohm resistor drop to get 2.5 milliamps to flow through it? Right? You understand that? So I did the math, and we came up with what? We came up with 250 millivolts. So when I measure 250 millivolts across that 100 ohm resistor, what's my load current? My load current is 2.5 milliamps. And that's what we're trying to do. And what we're going to do now is we're going to measure the Zener voltage, right? So what am I supposed to have on my input voltage, guys? Does it say? Yeah. I cannot regulate at 5.1 volts with a minimum input voltage of 5 volts. Your input voltage, you're unregulated. Your input voltage is always got to be greater than your Zener voltage. So my minimum I would ever put in would be what? 6 volts. The maximum I'd ever put in would be what? 7. Okay. So what y'all are doing is you're getting the Zener voltage confused with my input voltage, right? So did the lab say what my input voltage is supposed to be when my load current is maximum? Did it say that? I don't have the lab. Y'all got the lab. So right now we have no. What we're trying to do, adjusted rheostat connection sign. So right now we came up. It doesn't say. So what we're going to do now, guys, is we're going to measure the output voltage. So this is 250 milliamps, right? I'm sorry, this is 2.5 milliamps. Everybody okay there? Okay. And then I'm going to measure the Zener voltage. Yes, 2.5 milliamps. That's 250 millivolts flowing across a 100 ohm resistor. Right? You understand? So this is 2.5 milliamps flowing through the load. Right? Don't look at in your mind. What do you need to do? You need to shift my meter to the what? Left 2 times. Right? So up there it's millivolts, but we're doing 2.5 milliamps. That's what we're setting for, right? Y'all understand? So when this guy right here measures what? When this guy here measures 250 millivolts, what would A measure? 2.5 milliamps, right? Okay. And this is a technique that we use all the time. If I've got a resistor that I can measure across, instead of breaking the circuit and measuring amps, I am going to measure across the resistor and calculate current. Why? Because you have to break the circuit and measure amps, right? You understand that? So in your mind, when you calculate, and this is what's nice about using a 100 ohm resistor, is you just measure the voltage and move the decimal point to the left twice, and automatically you got what? You got the current flowing through it. Everybody okay? Okay, so here's our Zener voltage. So I'm going to measure across the Zener, which is our output voltage. And this is minimum current, right? This is my Zener voltage. So it's about 5.1. Yes, no? Yeah. Are we okay? Any problems? Questions? Are y'all writing this down? Or do y'all have a chart y'all got to write this down in? Okay. Yeah, because we're. Are we okay? Any questions? Okay, now I want to set my load current to maximum. What should I do for load current maximum? What should my meter read? What's not 7 volts? 7. There you go. Thank you. 700 millivolts. Okay, so here we go. There we go. That was pretty good, right? Oh, this is going to be touchy, guys. Okay, guys, this is about the best I can do. So now I'm going to measure the output voltage again. This is out of the load minimum. Are we okay? I got my meter leads backwards, guys. It's no big deal. 5.02. We're probably going to have to carry this out, guys. So this Zener's, y'all understand? So this is my input voltage. This is my load voltage. So what's this? 5 volts. Yeah, that's the minimum. That's the max current. Right? So I got 7 milliamps, right? So this guy's going 5.1 to 5 volts, right? Huh? What'd you say, Austin? Yeah, we might. That's what I need to do. Let me pause this and bring. First of all, we have to start off with a power source, right? Yeah, and of course we're using TDA here. And then what do we go to next? We're probably gonna have a watt. Enter. Then we're gonna have a watt rectifier. Then we'll have a regulator. Oh, I'm sorry, you're right. Filter. I was just making sure I was paying attention. And then we have a regulator. And then we have our output over here. And you can, I mean, we could come over here and our power supply could end right there, right? Y'all understand? I mean, it could end right here if all I wanted was a half wave or full wave power supply. The more you add, the more expensive your power supply comes to. But electronic devices can't handle that. A light bulb, a resistive load can handle that. So if I was going to run a resistor, you know, or something like that, or a motor, motors don't care, right? You understand? Motors don't care. They don't care if it's filtered or unfiltered, right? You understand? They'll run off half wave or full wave just fine. But if but I can move to here. So your power supply might end right there. Your DC power supply might end right there. If I did not need a regulated voltage, right? But I needed more voltage out than what half wave would give me. And then of course electronics would be over here. Electronic devices like a nice steady power supply. So this is where we'd end up with electronic devices. So I'll run this off and give this to you. This is the power supplies for the trainer. For this trainer right here. This is the power supplies for the trainer. So we start off with our watt. And here's start off here. Then this is our transformer. This is what we call a multi-tap or multi-winding transformer. So it's got several secondaries on it. It's got this guy. Then it's got this one. So this is what we wire our circuits up to. Is there's your transformer right there. So when I come up here and so when I come up here and connect to this right here, there's that transformer right there. 12.6 volt center tap transformer. That's it right there. Okay. Now this looks kind of strange because they got the drawing of a full wave bridge, but it's not a full wave bridge. It is a full wave center tap. What you mean? VR1? It won't let me go down there. VR2, this is a full wave bridge. Full wave center tap. They're using a bridge rectifier, but it's running as a full wave center tap. Now what the telltale sign is, notice what's missing here. Well, this guy's got this center tap connected to common. And notice this guy here does not have a ground. It's got a ground over here, but all these guys this is not ground. They didn't bring it through, right? You understand that? So it's technically a common. So what we have is this is my positive power supply right here. And then this right here is my negative power supply right there. You understand that? Yes or no? Yes or no? And we got our secondary right here, right? And it comes in here, and they bring it in here. What we got is we got this right here. And what we have up here is we have this. If I draw them right. And then down here, we would have this. So if you look at this, here's the anode. Here's another anode. Then they're what? They're connected together, and then this comes over there. So here's your positive power supply right here. And then if I look at this one, this has a negative, this has a negative. So this would be your negative power supply right here. So instead of this be connected to common, it comes out here, and then we should have what next? Should have a what? Filter, right? And then we should have a regulator. Now this is using what we call a 3-terminal regulator. So all the electronics is inside. So this right here would be unregulated in. And this should be what? Regulated out. And normally on these guys, they have what they call a post filter, which is going to be a little tiny filter right there. And what it does, it makes up for the regulator trying to regulate. Okay. What does the regulator do? Can anybody answer Kelvin's question? It's the device that we just did it. So the Zener diode is a regulator. What's that? Right. We just did a regulator. We called it a Zener regulator. So even though my input a while ago was changing between what? 7 and 6 volts, my output load was changing between 2.5 milliamps and 7 milliamps. My output voltage stayed within 5.1 volts, 5%, right, the whole time. So it's regulating the voltage. These are voltage ratings. With varying inputs and also with varying loads over the design. So what does that mean? If I tried to get 500 milliamps out of that load, that Zener is going to go out of regulation because we designed it to handle the load between what? 2.5 and 7 milliamps. If my input voltage drops down to 4 volts, it's going to go out of regulation because we designed it to handle an input varying voltage between what? 6 and 7 volts. Yeah, for power supplies, it's going to do it. Over your design. You can't say it's infinite, right? It's going to try. There's no such thing as 100% regulation. So we're not going to come up with one that's got a percentage of error of 0. So what we're doing is we're using these regulators. We're using 7800 series. These are positive regulators. And then we're using 7900 series. These are negative regulators. So I'm using, up here we're using a 7812. What do you mean? Yeah. So what we'd, over here, we would come in like something like this. So I'd point my cathode toward the input. Let's just do a half-wave rectifier. I would come over here and I might put a resistor there, and I would put my Zener in the circuit like this. And then this would be my output, right? And then we'd have a filter right here. I'm sorry. So this would be the way the Zener regulator would look. And this would be a negative regulator. Now, why do we need negative voltages? Well, for one thing, my wife has got an inverter in her. She has a 120 volt plug in her van. Huh? What's that? No, I didn't do it. It came with the van. You can go out here. You can go out here to Best Buy and you can buy what they call an inverter, which you can hook. Yeah, Best Buy's still around. Best Buy's doing pretty good. You can hook this up to your car battery and you can get 120 volts off out of that. So you figure, not necessarily. I'd put it across the battery. All right. So how in the world can we get AC from DC? What's AC? Yeah, but it changes direction. Well, the only thing I can do is I've got to have a plus DC to get this from, right? You understand? And then I've got to have a minus DC to get this from. And then if I have a plus DC and a minus DC, I can use electronics to generate an AC sine wave, AC waveform. Right? You understand that? So that means somehow I'm taking plus 12 volts and I'm running it through an electronic circuit that generates a plus and minus voltage. So the only way you can get AC, guys, is to have a what? A plus and minus voltage. What type of signal is going to the speakers out there on your car for your radio? Is it DC or is it AC? It'd burn up if it was DC. It is AC. So how does this do it? Well, inside your radio, it's got an electronic circuit that somehow generates a plus and minus DC out of AC. I mean, plus and minus DC out of AC. So to generate an AC signal from DC, we've got to have what? We got to have a plus and a minus power supply. And we do have some solid state devices that work off minus. So we can do that. So I've got a function generator over here. No. The only thing in your car, well, no, because what happened, yeah, but what you got on your alternator, so the alternator's doing this, and then what are you running it through? You run it through a what? No, you run it through a rectifier. And then you run it through a what? Then you run it through a regulator, right? Well, let's look at the filter. So this is your filter. So AC, we come in off this, then we run it through a what? Rectifier. Then we run it through a filter. Guess what they're using for a filter? Your big old car battery out there. Oh yeah, car batteries make great filters. And then what do? So we rectifier, right? Then we probably have a what? Regulator. And so this would be your DC out here. So it's using a battery. Batteries make really good filters. Because what happens is that they try to maintain a constant output, right? You understand? So if the voltage goes up, they just conduct more current. So this is your rectifier. So yeah, everything in your car operates off of DC, but we have an alternator out there, but we're going through the same thing, right? You understand? First of all, we have a watt out there. We have a rectifier. What are they using as a rectifier? It's diodes, right? Okay. Then we're filtering with the actual battery of the car itself. It makes an excellent filter. Then we run through a regulator, right? So this is really neat. You know, you can look at your alternator of your car, your output. About what voltage should you measure out of your alternator? What DC voltage should you measure when your car is running? Anybody know? Huh? About 14 volts. So your alternator regulates at about 14 volts. Yeah. So 13.7, yeah, but it should be over 12 volts, guys, because it's got to charge the battery, right? You understand that? That's right. Which means either your battery's got a short in it, it's not doing the filtering job, or your alternator's not putting out what it's supposed to. So yeah, you can check your alternator right off the bat. Just look across your battery, crank your car, let it run for a little, and you can check your battery, right? So you unplug your battery. I mean, you turn your car off. Then what should battery measure? As soon as you turn your car off, your battery should measure around 13 volts, and then overnight it'll go back to around 12. So as soon as you turn it off, it's going to measure a little high. They called it a surface charge or something like that. When you what? Yeah, your alternator output will probably still be there just because of the residual magnetism in the battery in the alternator itself, but it won't be near what it's supposed to be. So normally when we check the alternator, we keep everything plugged in. So what we do is we crank our car and measure across your battery, and it should go up to pretty close to 14 volts when the car running. Huh? What's that? Yeah, you couldn't run anything off the alternator because without the battery, because that's where it's getting its. Yeah, well, first of all, you're not going to get near the spark. It would surprise me if it runs long at all. Yeah. Well, if you get the batteries, if you get it started, so I was wrong. If you start it and then unplug your battery, it should run fine. Because the alternator, if it goes, if you yeah, but now that's dangerous, guys. Unplugging the battery, undoing the battery while it's running. But if you take the battery off and it goes dead instantly, that means your alternator is totally dead. Because the alternator, yeah. But you don't have to do that. Yeah. I wouldn't. I wouldn't do that. I wouldn't. I wouldn't unplug. I wouldn't take the cables off my battery with the car running. Well, so what day did you miss? I can go back and correct it. But y'all supposed, if you come in late, guys, what you're supposed to do? You're supposed to let me know you're here, and then I'll make a little note. And then when I go back and do the roll again, okay, guys. So let me do, okay, y'all go ahead and take a break. What time is it? Okay. Then y'all come back and I'll tell you what we're going to do about the test.